Hi friends, welcome to my channel in series of the advanced RTL coding. So without wasting much time, let's move to understand the RTL design problem 1. So the problem statement is like we have 8-bit input data and valid, and we have to send 2-bit output at a time with the valid output. And if the valid input valid comes before 4 clock cycle, like if there are uh, less than 4 clock cycle difference between two consecutive valid input, then there should be an error flag, because 8-bit data sending in 2-bit will take minimum 4 clock cycle. Yeah, so that is the port lists of the design: clock, reset, input valid, data input, and these are the output: valid error, valid output, and data out. And this is the FSM I have designed, that how the state transition should look like. Uh, Initially we will be in the idle state when input valid comes, then we will move to data state. Otherwise, when valid equal to 0, then we will stay in the idle state. In the data state, if count is less than 3, I will be running the counter 0 to 3. If it is less than 3, then I will be stay into data state. Otherwise, when count equal to 3, I will move to the idle state. When I am into data state, at that time if any valid comes, then it will be error condition, because we are still sending the data. So we will move to error state if valid equal to 1. In the error state, if again valid equal 1 come, then we will move to data state and check if till count 0 to 3 it there is no valid. It will send the data along with the valid output. Otherwise, in the error state, if in the error state there is no valid, then again we will move to idle state and check if any valid comes. Otherwise, we will stay into the same idle state. That is the FSM state. You can take the snapshot of it. I will be moving now to the RTL code. You can think of and design by your own. I will pause my video. Okay, so let's move to the coding of this FSM state. So here I have declared one data in register where I will be capturing the data in at the valid when valid is asserted. And this is count 2-bit counter 0 that will count 0 to 3. And this is the reset count. When the count will reach to 3, the reset count will be asserted, this at line number 46. And here I have declared the FSM states: S idle, S data, and S error in enum. So the enum properties is like it will automatically declare in the sequential number, incremental sequential number. So S idle will be 0, S data will be 1, S error will be 2. And the name of enum is current state and next state. Okay, so here this is synchronous reset. I am designing in system Verilog, so it is equivalent to always block. If reset is there, then in that time in the current state should be assigned with the idle state, and data into data in register should be 0. Else current state should be assigned with the next state, and if valid input is there, then store the data into data in register. Okay, and here this is the transition state transition implementation, state transition implementation. computation into combinational circuit. Okay, now how the state transition should happen? It is same what I have drawn here. In the idle state, when valid is there, you have to move to the next state, S data. When there is no valid, you have to stay into the same state. When you are S data state, if again valid comes, you will move to the error state. You can see here, if valid comes, you will move to the error state. Else, if count equal to 3, then you will move to the idle state. If count equal to count equal to 3, sorry, yeah, from here, if count equal to 3, you will move to idle state. Understood? Else you have to extend to semi state data if these two conditions are not correct. Now, if you move to error state, in the error state again you got the valid, then move to the data state and check if again any error comes, then you will move to the error state, otherwise you will start the counter and count till 0 to 3. In the error state, if this condition is not true, then you will move to idle state. So basically in error state you will stay only for one clock cycle. Okay, so now how, what are the activities, what are the signals need to be asserted into this state that I have implemented here. If reset, then count equal to 0. Else, in the case statement, if current state is s idle, then count is 0. If s data, then if recent count is asserted, then count equal to 0. Else count equal to count plus 1 and valid error, because in we are sending the data, so valid error should not be asserted. But when we are into error state, then at that time count should be 0, and now we have to implement the outputs valid error, valid out and data out. So you can see valid error will be asserted only when your current state is into S error state, and valid out will be asserted only when you are into S data state and there is no valid error and there is no input valid, so your valid out should be asserted. And data out is basically doing the bit slicing. So count, when count is 0, so your initial index will be 0 and width should be 2, so 0 1 your initial data. And if count equal to 1, then your initial index should be 2 and 1 more because width is 2, so 2 and 3 will be sent when count equal to 1. And when count equal to 2, 2 to the 4, 4 and 5 should send. When count equal to 3, 3 to the 6, 6 and 7th bit should be sent. So that is how the output should look like. So this is whole code. You can take the screenshot. I will be scrolling down to this code. Okay, this is the test bench I have implemented. I have asserted the valid and the d in data input and generated the clock and the reset, and this is the waveform. So you can see data in is changing and sorry, d in is changing, and in data in I will be capturing the data when valid is asserted. Okay, so you can see here the valid is continuously high for at least 1 2 3 4 5 clock cycle. So Since valid is started and is continuously high, so there will be valid error. You will be moving to stata state, sorry, stata state, but you see again in stata state the valid in is high. You will move to S error state. In S error state, you will see again the valid is high. You will move to stata state, and again you will see S error is high. You will again see the error. So valid error will be asserted when you are the S error state, and you can see there is no valid out. So there is no out valid output. The data out will is changing. You can see, but there is no valid out. So it means there is no valid data is going out at the output uh, port. So here you can see again the valid is asserted. So from we went from S idle state to stata state, and the same time we captured the D in into data in. So at that time data in was 63. So you can see 63. So last two bit is uh, 3. So at the data out, the first data is 3, and the next 2 and 3 bit is 0. So next data out is 0, and next fourth and fifth bit is 1 0, means 15 and 4. So it will be 1 0 means 2, and again 7th and 6 is 0 1. So this is 0 1 data. So till here you can see this valid is out, valid out is high. So first valid data is 3, second valid data is 0, third valid data is 2, and fourth valid data is 1. So here basically the data will be captured 1 at this valid, and at this valid the 2 will be captured, and at this valid this valid 0 will be captured, and at this valid 3 will be captured, and here it will be read valid as 0 because transition is happening here. So here the first valid will be received in this clock cycle, and the data will be 3. Okay, after that you can see the data is changing, but there is no valid out. So the data is there on the data bus, but there is no valid with the data, so that is invalid data. Okay, so here after count 3 the valid comes, so there is no valid error. So that is how it is implemented. And again you can see here valid error again is asserted, because if you see counter value, it is 2 when the next valid is coming. So at that time the valid error will be asserted, because count is not completed yet from 0 to 3, and the next valid arrived. So that is how the valid error flag will look like. Okay, and so that is the design. And in the next you can more make it automated design by parameterize it, like data width you can give any data width you want, and the output data you can output any data. So here you have to make it more parameterized. So that is the next assignment. I will make the video on that also. Till that, goodbye, and thanks for watching the video.